Thermal conductivity. Take a metal rod XY, place its one end X in a steam chamber at temperature T1 and other end Y in a calorimeter filled with water at temperature T2. Insulate the open part of the rod so that heat may not be lost and that quantity of heat may be found which is reaching from X end to Y end in time T. It is found from experimental observation that transfer of heat depends on the following factors. Cross-sectional area of the rod. Larger the area of cross-section A of the rod, greater will be the transmission of heat Q. Q directly proportional to A. Difference of temperature between the two ends of the rod. Greater the difference of temperature T1, T2, greater will be the quantity of heat reaching from one end to the other end of the rod, so Q directly proportional T1, T2. Time. In longer time T, more heat Q will flow across the rod. Q directly proportional T. Length of the rod. Shorter the length L, greater is the quantity of heat Q which reaches the far end. Q directly proportional 1 over L. Combining the above four factors, Q directly proportional A into T1, T2 into T over L, or Q is equal Ka into T1, T2 into T over L, where K is a constant of proportionality which depends on material of the rod. This is called the coefficient of thermal conductivity. K is equal QL over A into T1, T2 into T. If the equation area is 1 meter square, difference of temperature is 1 Kelvin, time is 1 second and length is 1 meter, then K will be equal to heat Q. When a meter cube of a substance is maintained at a difference of temperature of 1 Kelvin, then the quantity of heat that reaches from one end to the other in 1 second is called the coefficient of thermal conductivity of that substance. Material objects whose K has large value are said to be good conductors, and those having less value are called insulators.